You've learned a little about the forces between magnetic fields and charged particles, and you've learned something about the magnetic field that comes from a long straight wire. We're going to look at a specific way of putting those two things together, the force between parallel conductors. Here's the overview of how it works. First, we got a wire. It's got a current going from left to right in this case. That's what the picture on the bottom represents. Okay, so you got a long straight wire. It's got a magnetic field that goes around it when current passes through it. Use the curly right hand rule, so it's going to make a circle that goes around it that's always going to be perpendicular to the wire as it goes around it. In other words, as it goes from the top of at the top of the page, it's going to come out toward the viewer. Above the wire, it's going to go out the top toward the viewer. Below the wire, it's going to go into the page toward the viewer. That's what you should expect. If there's a wire parallel to it that's in the same plane, then the magnetic field that's made by the wire is going to be perpendicular to it. So that's the ideal situation. Remember, if you're going to, that when we look for the effect, when the magnetic field's perpendicular to the movement of charge, then that's going to be the maximum amount of force we can get. Okay. So if the current's going to pass through both wires, if the wire that's parallel to the other wire, which is perpendicular to that magnetic field created by the first wire, is going to act, then we're going to get a magnetic field that's going to put a Lorentz force on it, the kind of forces that we've calculated in the past. Okay. But that means that they're going to put a force on one another. Seems confusing, that's for sure. So let's look at a couple of examples to get a feel for how that actually works. First, we're going to have two wires that are in the same current direction. They're both going to be located in the plane of the screen or the plane of the page if it's a piece of paper. There's wire 1, again going from left to right. If I take my right hand rule, it's going to curl down so that and underneath the wire in the plane of the page, it's going to make a magnetic field that goes into the plane of the page or the plane of the screen in this case. Well, that's where my wire is coincidentally. And that current is going in the same direction. Well, now I'm going to use my flat hand right hand rule or whichever version of it with the fingers or whatever you'd like that does it. Okay, which means that I'm going to have I'm going to use in my case, I'm using my thumb pointing to the right, and then I'm having my fingers pointing into the page. That's going to give me an upward force. So there's going to be an upward force on wire 2 that came from the magnetic field of wire 1. Well, that's great, but remember that wire 1 is not the only one that can provide a magnetic field. Wire 2 is also going to provide a magnetic field of its own, and it will act on wire 1. So again, now we use the curly right hand rule the exact same way. We go up toward wire 1, and you can't see me, but I'm actually curling my hand with my thumb pointing in the direction of the current in wire 2. And hopefully you're doing the same thing, and it's going to make, and you can see that the current or the magnetic field is going to come out of the page toward you. You can see from the little dots that that's the direction that it's going. So now I'm going to use my flat hand to figure out what the direction of the force is for it. My thumb is pointing to the right. My fingers are pointing out of the screen, out of the page in this case. That's going to make a downward force. So you can see that actually the wires themselves are actually both attracting as they do that. Kind of weird. If you're not sure you follow, just rewind it. Watch the example again until you get it. The next example is one of two wires with the opposite current directions. I know that maybe you could just follow the exact opposite of the first one, but I think it's instructive to hear both of them. Okay, wire 1, he's back. He makes the exact same magnetic field below that it made the first time, one that goes into the page. This time though, we're going to have a wire that goes the exact opposite direction. So again, now I'm taking my right hand, I'm putting my fingers into the page or into the screen. My thumb is pointing to the left, so my hand, using the right hand rule, the cross product of those is pushing down. So I have a downward force in the plane of the page. It's actually pushing wire 2 away from wire 1. And I'm going to have exactly the same effect from wire 2 on wire 1. Opposite direction, but it's going to push away. And I'll show you how that happens. If you use the curly right hand rule with wire 2 from above, you get a magnetic field that goes into the page around wire 1. So then I take my regular flat hand right hand rule. I have my thumb pointing to the right. My fingers are going into the page. It's going to make my palm point upward. It means there's an upward force on that wire. So again, the opposite current directions are going to push away from each other. If you're looking for a thing to memorize so you can get these multiple choice questions right, this isn't a bad thing, but I want you to understand the mechanism by which it happens. Of course, there's some algebra that goes with this too, and it's not terrible. It's two equations that you've already used. First, we need to calculate I'm only going to look at one of the examples since they're both exactly the same, and then generalize them into a general case. So I'm looking at the field from the first one, okay, and that's just mu naught I over 2 pi r. We've derived that before, mu naught I over 2 pi r. It's something that you've seen. So we're calculating that out, and we're going to use that magnetic field in the equation F equals ILB. Again, another derivation of F equals QV cross B. They're perpendicular, so QV cross B is just QVB, and we're replacing QV with IL. I said I2 because it's the second wire's current that matters here, and L2 because it's the length of the second wire that matters. Then I subbed everything in with its constituent components, where I said F2 equals I2 L2 mu naught I1 over 2 pi r. And again, those are all the little components put together. And then I generalize it down here for all kinds of cases, where I said that F equals mu naught I1 I2 L over 2 pi r. I say L because usually the two wires are of the same length when you do the problem. It's pretty tough if they're not the same length. But if they're not the same length, then it's the length of the second wire, the one that you're looking for the effect on, if you have to do it that way. That should be enough with plugging numbers in. And remember, R is the distance between the two wires. That should be enough to solve all of the problems that are related to this topic.